Okay, we are on chapter 16, and we've been talking MX, that's what we've been talking about. So last time we got into Gibbs free energy, which is delta G, and that is Gibbs free energy. That is energy available again to do some type of work. And there are multiple ways that we could kind of calculate delta G. One way is just like kind of normal. You could take delta G of formation, and you basically take your delta G of your reactants, I'm sorry, your products, divided by the delta G of your reactants. Again, you could look it up in a table, these values. You want to multiply by the coefficients like normal and add them up. And one of the nice things about delta G, as we talked about, is actually unlike sort of delta S, where you have to calculate delta S of the universe, you can actually use the delta G value to determine spontaneity. If the delta G is a negative number, then the reaction should be spontaneous. It should head towards the product side. If delta G is a positive number, then it's going to be non-spontaneous the way it is written and kind of will hang out on the reactant side. There's also another delta G sort of equation. Delta G equals delta H minus T delta S. And this has obviously delta H and delta S in it. So a reminder that for delta G, again, I would kind of choose whichever equation matches sort of the information given to you. So if you have the delta H or delta S, you could go into this equation here. You do need to be careful of units. Again, kilojoules are typically the units of delta G. Delta H is also kilojoules. Delta S, remember, though, is joules. So when you're using this equation, you do have a unit issue. Again, you can convert them to joules. You can convert them both to kilojoules, but you do have to do some type of conversion. Otherwise, you will be off. And obviously here, this temperature in Kelvin needs to be in as well. Remember, depending on sort of the signs of H and S, you may need either maybe a low temperature, a high temperature to be spontaneous, or a regular temperature will be spontaneous depending on those signs. Any questions on that there? All right, so I think where we laid up there was right around here, and it's been a long time since we talked about equilibrium, so we can't leave that guy out. So we can relate our delta G to also the equilibrium constant. And for example, here we do have this equation here, number 3, with delta G's in it. Delta G is equal to delta G naught plus RT natural log of Q. These are two delta G values, and really the difference is that little naught that we sort of talked about. That naught usually means standard conditions, and that usually means that you calculate it kind of from a table. So this delta G is, for the most part, that delta G of the products minus the delta G of the reactants that you could get from the table if it's not provided for you. The R here is a gas constant, but it is the 8.314 version of it, the one that has energy. So you want to make sure you don't use obviously the one for gases. And T here is temperature in Kelvin. And Q is our reaction quotient. So that again is calculated the same way that we calculate K. It is products divided by reactants. So what is the other sort of delta G? This delta G is, you can think of it as like being under non-standard conditions. So there's something that is really not happening under standard conditions. A reminder that standard conditions basically means 1 molar if you're dealing with concentrations, 1 atmosphere or 1 bar if you're dealing with pressures, usually 25 degrees Celsius, but those are really the two big ones there. So if you come across a problem where you're dealing with something where the concentrations are not 1 molar or not 1 atmosphere for pressures, then you would probably want to use this sort of equation. So this is sort of your delta G equation when there's something that is under those kind of non-standard conditions. Now, if we get to equilibrium, what happens at equilibrium is the above equation, delta G equals 0, and Q is actually the equilibrium constant. And that top equation then becomes this equation here that relates the delta G to the equilibrium constant and is minus RT natural log of K. And this again is our delta G under standard conditions in this case. So, couple things people always kind of screw up on these equations. First off, this one is a plus, and people forget the minus here. So again, those are very common sort of errors when people do this. So again, obviously, if you have any type of problem that deals with equilibrium constant, this would be the equation to use. You got kind of non-standard conditions, this would be the equation to use. You got, like we saw where we were just talking about a second ago, you got H and S, this would be the equation to use. And frankly, if you just have a formula or an equation and nothing else, probably go to the table and use that one for the delta G. So again, there's obviously here 4 different sort of equations or formulas that have delta G in it. My best advice is, like I said, kind of choose the one that matches the information in the problem, and that's probably the right approach there to take it. Any questions on that there? Let's see here. The good thing about this equation here with the K value is if you understand the equilibrium constant, which I hope you do at this point, you basically could just follow the same thing. So for example, if we have a large value of K, that should mean we mainly have products. And the only way to kind of get the products is delta G should be negative in that case, right? A spontaneous reaction heading towards the product side. Opposite is true if you got kind of a small value there of K. We would mainly have reactants at equilibrium, and it will kind of go to the left there. And in that case, our delta G would be a positive number. So again, all those things should sort of agree with each other. If you have a negative delta G, which means the reaction is spontaneous, you should probably expect to have a lot of products, and that should also mean that you probably should have a larger value of K. If you have a delta G that's positive, that means the reaction, the way it's written, is basically non-spontaneous. It's going to probably hang out on the reactant side, which means you should have a smaller K value. So if you're ever doing a problem, for example, and you calculate delta G and is positive, but then end up with a large value of K, something is not right there, probably in the calculation. Again, those things should agree with each other. So why don't you try one here and see what you come up with. We want to calculate the equilibrium constant here. These are the delta G of formations there that you could get from the table. Take a few moments there to see what you want here. We obviously are looking for an equilibrium constant, so that should direct you probably to this equation here, which is the one that has the equilibrium constant in it. That means we do need to calculate delta G in this case. So since we just have the equation, obviously we would go to the table and look up the values, and we'll basically do our products minus our reactants. So again, we want to add up all of our products and then subtract it from our reactants. Remember, we do need to take the coefficients into account when we do that. So for our product side, that would be 3 times our 0 here, basically. We're then going to minus it from our reactants, which is 2 times our O3, which is 163.4 kilojoules. And that's going to give us a delta G here of 63.4. Looks like negative 326.8 kilojoules. Our temperature here is 298, as we need to add obviously our 273 there to convert it to Kelvin. R we always have, which is the gas constant, again, the one that involves energy. So putting these values in, that'll give us basically minus 326.8. I am going to multiply it by 1,000, and I'm going to do that to put it into joules. And the reason I'm doing that is because R is in joules as well. So again, if you leave 1 in kilojoules and 1 in joules, you're going to have an issue, obviously, with units. So negative here, 8.314. And our 298 Kelvin and our natural log of K. So I'm going to basically take all this and divide it over to the other side. And if I do that there, I will end up with a number perhaps here. I'll end up with about the natural log of K is equal to 131.9. Again, to get rid of the natural log, we're going to E both sides. So we're going to take the E of both sides there. And that's going to give us, I'll go up on top here, it gives us a K of about 1.9 times 10 to the 57 in this case. Yeah. Any questions on that there? Again, you got to be careful of negative signs, right? Otherwise, obviously, when you do the inverse of the natural log, you're going to be in some trouble. Again, based on what we see here, our delta G is negative, which means this reaction is spontaneous, right? And should head to the products. Since it heads to the products, we should have a larger value of K. And I would say that qualifies as a large value of K in this particular case. Any questions on any of that? So again, that was what I was talking about earlier. Again, those values should agree with each other. Any questions on that? All right, let's try another one here then. Try this one here. Calculate the delta G for this reaction. If the KSP is 1.7. Okay, so on this one, we're looking for delta G. We obviously have a K. It doesn't matter what type of K. So once again, probably our same equation would be a good one. In this particular case, we actually have everything on this side, so we just need to plug in, I think. So minus our 8.314 Kelvin mole, our temperature 298. Obviously, we need to convert that by adding 273 to it. Natural log of 1.7 times 10 to the minus 6. Once again, it doesn't matter what type of K value it is, they're all K values. So we'll take the natural log of 1.7 to the minus 6. We're going to times it by 298 and also times it by 8.314. And then we're not going to forget the negative 1 there. And that's going to get us here a 32,914. These are in joules based off of that. So obviously, if we convert it to kilojoules, we're looking at about 32.9 kilojoules. This is a positive value for delta G, which means it's non-spontaneous, and that's good because here we have a small value of K. So again, all those things should agree with each other. Any questions on that there? Technically speaking, you could have left it in joules if you wanted to. It's okay. But usually delta G is given in kilojoules and delta H as well. Any questions on that one? All right, one last one here to wrap up this. Okay, so on this particular one here, they do give us delta G naught. We are actually looking for delta G. So this is going to be our sort of non-standard conditions where we have basically our two delta G's here. Remember, that's a plus RT natural log of Q. What makes this non-standard conditions is this right here, the pressures. So remember that standard pressures is 1 atmosphere. So here, these are not 1 atmosphere, and that's what sort of the non-standard conditions that are happening. So in this case, we need to get the delta G naught. They actually gave it to us in this problem. If they didn't give it to us in this problem, you would need to go to the table like we did on the previous problem there and do products minus reactants and basically calculate it. So we actually have that. We obviously have R, we have T. We do need to calculate Q. Q again is the reaction quotient. So that is again our products over our reactants. And we do it the exact same way as we do K. So we can either square it, and we got our H2 and our I2, except here we are obviously doing pressures, so we would do the exact same thing here, obviously, with pressures in this case. So putting our Q in there, we got HI is which one there? It is 0.23. We're going to square it. We're going to divide it by 4.26 and 0.024. That's going to get us a Q of looks like 0.517. I'll call it 4. Now that we have that, we pretty much have everything we need. We will go our delta G here is going to equal our delta G naught. So that's going to be 2.6. I again here, I'm going to multiply by 1,000 to put this into joules for this guy being in joules as well. So again, that we, have everybody in the right units. Plus our 8.314. Our temperature of 298 Kelvin, and our natural log of what we just calculated there is 0.5174 in this case. So we'll do that there, natural log of that. We're going to times it by 298 and times it by 8.314. That's going to get us here negative 1632.5. And again, these are in joules. And on the front end there, obviously we times that by 1,000, we got 2,600 joules happening. So that plus our number there is going to hit us with a delta G that's 967 joules in this case, about 0.967 kilojoules if you want kilojoule unit. First off, any questions on that there? In this particular case, this reaction under standard conditions is non-spontaneous, and even under these conditions, it is still non-spontaneous with a positive value for delta G. Any questions on that one as well? All right, that wraps up, I think, chapter 16 in thermodynamics. Off to the next chapter, I think. If I can find 17. And that's about electrochemistry. So really this chapter is about sort of galvanic cells and stuff like that. But we're gonna first off kind of, maybe it'll be some review for you, depending on maybe who you had for Chem 50 and stuff. We're gonna talk about redox reactions, talk about balancing redox reactions, oxidation numbers, just to make sure everybody's on the same page before we get into kind of the real part of chapter 17. So first off, we're going to talk about redox reactions, and redox reactions means oxidation and reduction. And these things always occur together. So if somebody gets oxidized, somebody else will get reduced. Redox reactions basically are a result of an electron being transferred. Right. And electron being transferred is one of the three reasons why a reaction takes place. Redox reactions involve electrons being transferred, and that's one of the three reasons why, like I said, a reaction does take place. And again, it is the big classification of reactions, and they have more specific types of these reactions, as you may be familiar with. These are synthesis reactions, decomposition reactions, single replacement reactions, and combustion reactions. So all those kind of reactions fall under redox. So what does oxidation mean? Oxidation means there are several definitions, but the one we use most here in general chemistry is something that loses an electron, and reduction is something that gains an electron. And there are some other definitions. For example, oxidation can also mean that something gains oxygen as you go from reactants to products. It could also lose hydrogen as you go from reactants to products. And reduction can also mean the opposite of those definitions, which is losing oxygen as you go from reactants to products, and gaining hydrogen as you go from reactants to products. I would say in most cases, you probably won't come across these definitions too much unless you're off to organic, which may be our next semester. So if you're off to organic, those are usually the definitions of oxidation reduction we kind of look at more, which is either the gaining or losing of oxygen or hydrogen. But for here in general chemistry, a lot of times we look at losing and gaining electrons. So when something loses electrons, it becomes more positive, and when something gains electrons, obviously it becomes more negative. So some people like to remember this by Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. People nowadays are fond of the oil rig type of move, and oxidizing is losing, reducing is gaining. You put Leo the lion on the oil rig, he goes grr. You don't have to choose. You can just use them all together in one big old sentence there. So how can you determine if something is going through oxidation or reduction? There's actually a fairly simple approach, and I like to sometimes just use what I sometimes call a number line approach. And on a number line, there's 0, and then there's positive numbers and negative numbers. And when you look at the oxidation of an element from the left-hand side of the arrow to the right-hand side of the arrow, if you see its oxidation state or number is moving in this direction, the positive direction, then that thing is going through oxidation. And if you look at the oxidation number or state of something and it's moving in this direction, the more negative direction, that thing is going through reduction. So that's a very simple way to sort of do that. So for example, if we took some sodium metal and we took a little chlorine gas and we put it together in a combination or synthesis reaction to make sodium chloride here. This is a redox reaction that's occurring. Again, if we look at the oxidation state, as we'll talk about shortly, it's not necessarily the charge that things have, but it's similar. A reminder that anything in its natural state, uncombined, the way it naturally comes, has no charge or no oxidation state, basically has an oxidation state of 0. It is only when things sort of combine, especially when metals and nonmetals combine, that we start to get charges. And the guys over here actually do have charges. That's +1, and that's -1 for our chloride here. And if we look at what's happening and just kind of follow this number line here, we can see that sodium here started at 0 and ended at +1, which means it's moving in the positive direction. So the sodium here is going through oxidation. By the way, because it always occurs together, if you can confidently know one of these things happening, by default, the other guy is going through the opposite thing. So that is reduction. We could also just do it for chlorine as well. Chlorine is starting at 0 and ending at -1, which means it's moving in a negative direction. So it's going through reduction. By the way, the things that are being oxidized and the things that are being reduced are always found on the left-hand side of the arrows, right? So those are things that are happening. So what's really happening in this case, right, is this sodium is sending some electrons over to the chlorine. And again, that's basically what a redox reaction is in this particular case. We also should know this because sodium in this case is a metal and chlorine is a nonmetal. So if you just think about ionic compounds, that is always the situation. The metal is always the one that loses electrons and becomes a cation, right? Positively charged. The nonmetal is always the one that gains the electrons and becomes negatively charged. And that should always be sort of the case in this situation. But this also works, for example, if you had something like this, say iron 3 on the left and iron 2 on the right, is this being oxidized or reduced? So take a moment and decide here. So that's +3 and this is +2. So really our iron is starting at +3, which would be over here, and ending at +2, which means it's moving in the negative direction. And this guy is being reduced in this case. Yeah. Any questions on that there? So in an electrochemical process, such as a redox reaction, we actually use these electrons as they go out to do some type of work. It's very similar to obviously batteries. If you look at a battery compartment, there's a little wire, right? You put your battery in, and the electrons basically is a redox reaction. So those electrons go out, they power your device and go back around to the other side, on the positive to negative sort of side of your battery. Also why, for example, if you put your battery in backwards, it doesn't work because you just made your spontaneous reaction non-spontaneous by flipping around the wrong way, basically. So as that energy is released, a spontaneous process occurs. Here's another example. Once again here, magnesium uncombined has an oxidation state of 0. Oxygen, how it naturally comes, also an oxidation state of 0. When they come together here, once again, our magnesium is +2 and our oxygen is -2. So again, if you weren't sure, you could go to the number line here, starting at 0 for the magnesium, ending at +2, moving in the positive direction as we would expect here, oxidation occurring. Oxygen starting at 0, ending at -2, becoming more negative in this case, which means it is the reduction in this case. Now, we could actually write what are referred to as half reactions. And they're referred to as half reactions because they describe basically both of those things that are occurring, the oxidation half reaction and the reduction half reaction that's occurring. And they're half reactions because basically if you add those back together, you will get the overall reaction that's occurring. This first one is the oxidation half reaction. Again, our magnesium is going from 0 to +2, so it's losing those electrons. We know it's an oxidation half reaction because in an oxidation half reaction, our electrons are always on the product side. So we always have electrons on the product side in an oxidation half reaction, like they are being given off in that reaction. That over here are electrons on the reactant side, and that is our reduction half reaction, where we always see electrons on the reactant side like they are being gained. By the way, the number of electrons is the same in each half reaction, and they should always be the same in each half reaction because however many electrons are being sent over this way is how many electrons the oxygen should gain. So it should always be balanced in terms of the number of electrons. That's also why we have 4 electrons here, because each magnesium will lose 2 electrons, and we have 2 magnesiums. So that's a grand total of 4. So when you have these simple half reactions like this, you should always make sure that the electrons in both of the half reactions are the same number. If they are not, it sometimes requires you to multiply a half reaction by a common number. And sometimes you may have to multiply both half reactions by common numbers to get to the same. The reason for that is if we wanted to then go and add these reactions back together, anything that's on the opposite sides of the arrow can either cancel out completely or reduce. The one thing that should always cancel out when you add these together is the electrons. So again, you always want to make sure that they are the same numbers in each half reaction before you add them back together. And again, if they are not, you need to maybe multiply by a number. At that point, that's actually the only thing here that will cancel. Everything on the left stays on the left of the arrow, and everything on the right stays on the right-hand side of the arrow. These are 2 ions. They're going to come together basically to make our ionic compound here, magnesium oxide in this particular case. Any questions on that there? That's what we just talked about. Now, in addition to, as we just see here, same pretty much as the last slide, we have our things being oxidized and our things being reduced. There's also 2 other sort of names that come into play, and that is what is known as the oxidizing agent and the reducing agent. And the oxidizing agent is the substance that gets reduced, while the reducing agent is the substance that gets oxidized. So why is that? That is because the oxidizing agent will get reduced, which means it needs to gain electrons. And because it needs to gain electrons, it's going to cause the other guy to lose electrons and get oxidized. So it's causing the other guy to lose its electrons. So that is what is known as oxidizing agent. The reducing agent is the thing that gets oxidized. So because that guy is going to lose his electrons, somebody else will gain the electrons and get reduced. So it's causing the reduction in the other case. So as we saw a second ago, this is our thing that is going through oxidation. This is our guy that is going through reduction. And that means that the magnesium here is our reducing agent, and the oxygen here is our oxidizing agent. And again, those are different things if you're asked those things, and sometimes people get them confused. So if you're asked what is the reducing agent or oxidizing agent, that is a different question than what is being reduced and what is being oxidized. So you want to make sure you don't get those guys confused. Just like what is being oxidized and reduced is found on the reactant side, that is where you find your oxidizing agents and your reducing agents as well. Any questions on that there? Here again is another just example of what we've been talking about. And again, here looking at calcium, no oxidation state, no oxidation state. Once again, +2, -2. So again, we see what we expect here. Calcium starting at 0, ending at +2. So it is being oxidized. Oxygen starting at 0, ending at -2, so it is becoming more negative, it is being reduced. And again, in this case, the calcium here would be our reducing agent, and the oxygen would be our oxidizing agent. Once again, here we want to make sure we have the same number of electrons in each half reaction. And by the way, if you ever write half reactions, which you will, you should never have electrons on the same side of the arrow because that is not correct. So there always should be one on the product side, which is your oxidation. There should always be one that has electrons on the reactant side, which is your reduction. They should never, ever really in two half reactions have the electrons on the same side of the arrow because definitely they will never cancel out in that case, and one of them's incorrect. So as I mentioned before, our reducing agent and our oxidizing agents are basically opposite of their names. So the oxidizing agent is the guy that gets reduced, while the reducing agent is the guy that gets oxidized. So as we saw earlier there, and I just mentioned, the calcium is our reducing agent and the oxygen would be our oxidizing agent. Now, as I mentioned before, sometimes you can determine oxidation or reduction without necessarily looking at oxidation states, but just looking at, as I mentioned before, either gaining or losing oxygen or gaining or losing hydrogen. So if we were looking in this case, we could clearly see the tin here and the tin here. The difference is as the tin went from the left to the right-hand side, the tin here actually lost oxygen. And you can actually see in terms of carbon, as you go from the left to the right, the carbon actually gained oxygen. And because the carbon gained oxygen, that again is another definition of oxidation. And the tin lost oxygen, which means it's a definition of reduction in this case. So here, this guy is being oxidized. The tin here is being reduced. And because of that, the tin here would be our oxidizing agent. The carbon here would be, as it says there, our reducing agent in this case. Now, in this particular case, you don't actually have to do the oxygen gaining or losing because you actually had this guy there, basically. And you could actually just do oxidation states. That's -2 for oxygen. That's a -4. That is a +4 for our tin on the left-hand side. Right-hand side, this is tin not attached to anything, which is 0. And again, you could throw to the number line here and see the tin started at +4 over here and ends at 0, definitely moving in a negative direction, which obviously will tell you, as we heard there above, that this is being reduced. If you were able to determine that by default, the carbon would obviously have to be doing the opposite thing. So again, in this case, you still could kind of look at oxidation state and still figure out sort of the same thing. But there are some equations and reactions, again, very commonly in organic chemistry, where you deal with basically just carbons, hydrogens, oxygens, stuff like that. There's not a lot of metals or anything like that involved. It's sometimes easier just to look at the oxygen or hydrogen being gained or lost. Any questions on that there? So let's talk about the rules to assigning oxidation numbers. And just a reminder that you may be familiar with this, you maybe talked about it hopefully last semester, but just in case, let's talk about it. Oxidation numbers are oxidation states, which is sometimes referred to. They are essentially the charge the atom would have in the molecule if all the electrons were completely transferred. So the first thing about oxidation states that sometimes confuses people is the idea that at this point in your chemistry career, you have beat into your head that certain things on the periodic table have certain charges. And that is correct. You know, like group 1 is +1, +2, +3. And then group 5, 6, 7 is -3, -2, and -1. And that is correct in the sense of if you were making an ionic compound. And if you're dealing with an ionic compound, then basically the oxidation state and the charge would basically be the same thing for that particular ion. Now, what happens though when you are not in an ionic compound, but you're in a more covalent compound and things are sharing electrons, things that you normally associate, for example, as having a negative charge, like chlorine. We normally think of chlorine as having a -1 charge. But when chlorine hooks up with other nonmetals and actually are sharing electrons, based on electronegativity, something like chlorine can take on a positive oxidation state. So, for example, chlorine could be +1, +4, +3. It could actually take on a more positive sort of situation because it's sharing electrons with other nonmetals. And the difference in electronegativity is going to actually make chlorine, in that case, more positive than it would in an ionic compound. So keep that in mind. Sometimes oxidation states don't really match up within your head. We sort of think of charges for things. So let's talk about the rules. If you have, basically, as we kind of were doing these previous examples, if you have anything that is by itself, uncombined, naturally how it comes, the oxidation state is going to be 0. So a reminder as well, anything from the periodic table that's not attached to anybody else is a 0 charge, basically 0 oxidation state. If you have any type of ion and it has a charge, a monoatomic ion, whatever the charge is on it is its oxidation state. So for example, if we had like iron 3 from iron 3 chloride, then iron 3 would have a +3 oxidation state. So it'd be kind of the same as the charge. Our friend oxygen here is probably the best place to start with in most cases. And oxygen is going to be -2. There is a situation where oxygen is maybe not -2, and it's really because it's not necessarily oxygen, it's actually peroxide. And peroxide here is this guy right here, which is a polyatomic ion peroxide, like in hydrogen peroxide. So if it is something like hydrogen peroxide, for example, the oxygen is actually a -1 oxidation state. Other than that, you could almost 99% of the time safely assume if you see an oxygen, that is probably going to have a -2 oxidation state, and that's a good place to start with. How do you know it is peroxide? Well, usually, like we kind of see here, because it's really -2 overall, there's usually an extra 2 on the bottom there. Like if you have sodium peroxide, it'll be Na2O2. So there's kind of that extra 2 that kind of hangs out on the bottom to kind of tell you that maybe it's peroxide in that case. But again, I would say 99% of the time, you could probably just roll with -2 and it's just oxygen, you'd be in good shape. Now, hydrogen is usually a +1 oxidation state unless it comes after a metal. So if you had LiH, lithium would actually be +1. In this case, that's hydride, the negative version of hydrogen, and it would have a -1 type of charge. Everybody in group 1 is +1, everybody in group 2 is +2, and fluorine is -1. Now, when you add up all of the oxidation numbers in a particular compound, when you add up all those oxidation numbers, they do need to equal the charge on that compound. So if that compound is neutral, then when you add up all the oxidation states, they need to equal 0. If it is like +1 or -2, then they need to add up to +1 or -2 overall. So if we have something like bicarbonate here, and you want to assign some oxidation states here for each of the elements, I personally would say that if you have a 3-pack of elements like this, and you want to give the oxidation state to all 3 of them, I would save the guy in the middle for the end. Usually, if you have oxygen, start there, kind of go right, go left, and save the guy at the middle there for the end. So oxygen here would be -2. That oxygen is going to contribute, all 3 of them, a -6 charge. Going to the left-hand side, the hydrogen would be +1. So I basically have +1 and -6. In this particular case, because this is bicarbonate, it has an overall charge of -1. And that is what everybody should equal when I add them together. So at this point, I'm at -5, which means the carbon in this case actually would be a +4. That is a +5 -6 equals -1. So that all adds up perfectly here. Now, when you are given the oxidation states or giving the answer for the oxidation states, the way you should write it is hydrogen should be +1, carbon should be +4, and oxygen should be just what one individual is, not the grand total, So oxygen should be -2. So you should just give the actual oxidation state for 1 by itself. You also should, as I put there, include the positives and the negative charges. So if it's positive, you should put plus, and if it's negative, you should put negative when you're writing the oxidation numbers or states. Any questions on any of those there? All right, so let's take a look at a few here to finish up on here. So for each of these, why don't you assign oxidation numbers for each of the elements? So we have Li2O, we got PF3, HNO3, and Cr2O. Okay, so let's take a look here. So once again, I would start with oxygen. So it's just an ionic compound. So this is going to end up very much like we would assume, -2 here and +1. Again, in an ionic compound, pretty much the normal charges will be our oxidations numbers or states. Here, taking the PF3, fluorine is always -1. That's going to contribute a -3 charge here. And that means actually the phosphorus here will take on a +3 oxidation state. So again, as we can see here with phosphorus in an ionic compound, we normally assume phosphorus would be -3 as it's accepting those electrons. In this case, though, what's happening is it's hooked up with some fluorine, which is sharing electrons with it. And fluorine is the most electronegative element you could have, which means the fluorine is sucking the electrons away from the phosphorus and making it have a more positive oxidation state than what it does in an ionic compound, where it's the guy that actually receives the negative electrons, and that's why it becomes negatively charged. So this is what I was talking about earlier. In a covalent situation, things that we normally think about in terms of charges will be different based on the sharing of electrons, or really the unequal sharing of electrons and what they're sharing with. Here with nitric acid, we got -2. That's a -6. Hydrogen there is going to be +1. Again, in this case, this actually is neutral, which means this doesn't equal 0. So in this case, it is a +5 there for the nitrogen. So hydrogen would be +1, nitrogen would be +5, and oxygen again would be -2, not -6 in this case, would be the oxidation state. Any questions on that one there? Again, similar idea here. If you take a look at what nitric acid looks like, if you drew it, I won't draw all the dots in, but kind of looks something like this. This nitrogen, in this case, is going to have its electrons sucked out towards the oxygen. As you look on the periodic table, oxygen is further to the right there, more electronegative, going to make this nitrogen more positive in this case. Again, unlike in an ionic compound where the nitrogen would be receiving the electrons from the metal, in this case is actually kind of losing its electrons by unequal sharing with those oxygens. Here with our dichromate, oxygen is -2. That gives us a -14 for the oxygens. We do need to equal -2 overall, as this guy has a -2 charge. So that means there are actually 2 chromiums. So that looks like a +6 in that case for each chromium. And that would get us a +12, and a -14 is a -2. So in this case, chromium would be +6, oxygen would be -2. Any questions on assigning oxidation numbers? Being able to assign oxidation numbers are really important in this chapter, so you understand what's going on, who's being oxidized, who's being reduced. Any questions on it? All right, good place we'll lay it up